Now, another easy one to look at is if light passes effectively through the radius, what's its angle of incidence?
0,
0. So what's its angle of reflection?
0.
0. Because this point on the mirror that is directed inward toward the radius is exactly normal to the radius. At that point, it's like a plane there, at just that tiny little region. So any light coming in will reflect backwards through the radius point itself. Now, without even worrying about a third principal ray, all you need are two rays. If they're effectively drawn, convergence of two rays will give you where the image is, unless it's blurry. So this is where my image would be. Now let's look at a third principal ray. The third principal ray would be a ray that passes through the focal point. Now why, when it passes through the focal point, it continues on, and then it reflects back outward. Is it obvious why light passing through the focal point would come out parallel? Think about why that
Parallel
would be the
passes
case.
through the focal point.
What's that?
Because light that's parallel passes through the focal point. So
Sure.
It's just that
Or-
in the other direction.
Yeah, or if you will, if you had a light source here, all the light coming from this point
They'd all be perpendicular.
would all come out parallel. Now, this is only one ray of light that physically does that. All the rest of them are spread out. But for the one ray, it's as though an object at this focal point produced it. There's no distinction in terms of the direction of the light. So it comes out parallel. And ultimately, you put all of that together, you get a convergence. And it should be a convergence of all of the rays at some point in space. So this should be where the image is formed. I'm going to draw in red. I'm going to draw an image again from the optical axis. Since I reference the object from the optical axis, I'll reference the image from the optical axis. And I could do that at every other little point inside of this outer boundary point, which would just form images along the shaft of this arrow here. So I only need the end point to get all the information. Okay, so we have three principal rays. 1, 2, and 3. And you only need 3 of the 4, or you only need 2 of the 3 to generate or to find an image, but it doesn't hurt to have all 3. Now, a couple things that we can say about this image. First of all, the image produced occurs on the same side as the object. So, because of that, well, and there's a couple other things. The other thing is, if I were to put a piece of paper here, or some sort of a screen to look, and you should have seen this in the lab, I would be able to see physically what that reflected image looks like. It physically projects in real space. It's a real convergence. So we call it a real image. Because it exists. You put a piece of paper there and see it. Okay, our eye will play tricks on us sometimes. But when a physical image is produced, a real image that you put a piece of paper on and see it, we say it's a real image. Now, you might ask, why do you see it? If the observers out here look at, why would the observers see this? These are obvious questions that aren't so obvious in your textbook. If I were to remove all the rays except just the rays coming out from this point. Basically, what do we have? We have one light ray coming this way, one light ray coming this way, one light ray coming that way. as though they originated at a single point. Blow that up for a second. Here's my image. And from this side, all the light seems like it's coming out like this. And if there were any more rays, it would look like that. If I'm looking out here, what do I see? I see a source right here. That's no different than looking at this object. All the light coming out can be traced back to a single point right there. So an image to an observer looks just like an object. There's no distinction. The source may be produced differently, but it's the same dynamic as far as our eye is concerned. Effectively, our eyes trace light out, or light observed, back to a point of origin. If there's no point of origin, we don't see a focus image. Is that bizarre? It's kind of cool. So as long as I'm out here so I can pick up the reflected light, this point looks like a real object just sitting there, because the light that passes through it comes out as though it went through a single point. That's wonderful. That's kind of cool. Now, the other part of it is that for this particular example, the image is upside down. Because it's upside down, it will look upside down to the observer. You could sit over here and look at two things, say a pencil and its reflection. We would see a pencil upright, and we would see a slightly smaller inverted pencil. You ever stared at a spoon? Or ever looked at a spoon, I should say? I might have a mirror here that should pass around because it's really kind of cool. We have more than one. Okay, you gotta have one that's small enough to be able to see something. Is it in here? No. We used to have a nice makeup mirror, cosmetic mirror. We don't seem to have it. What you can kind of see would be that, and like I said, maybe you've seen these before, I'm not sure. But if you just take one of these jobs, and you look carefully. Hold it out away. Look at yourself. We'll be narcissists for a minute. And I don't have, I do have a little bit. You can have this. I don't know if you guys have these. Okay, that might be the best one to hand around. Okay, so if you look carefully and you hold it out away, you can see your image. Now you got to hold it out far enough. That's probably a better mirror. That one's a better mirror, so pass it around and look carefully. If you hold it up close, you see one image. But if you hold it back farther away, you see a different image. Spoons work great for this, believe it or not. Look at that one, that's a better example. Hold it farther away first of all. So you're outside of the focal length. Always somebody. Who's it?
Not really. This one's got a 2 minutes.
Yeah, that's. Hold it out away. Oh, I can see it from here. Look at your image. What do you say about your image? It's upside down and it's smaller than you are. I can tell from here. Okay, we'll let that pass around while we're doing it. But that image you can physically see, right? So for all the esoteric crap we drop on the board, it's something you physically see. Here's what's subtle about it. Believe it or not, if you look carefully at that image, it's hard to tell because that's a crappy surface. The image is actually in the front of the mirror. It's not behind it. Now, we're used to looking at every image inside a mirror. So we're sort of naturally conditioned to assume whenever you see an image, it's inside the mirror. But it really isn't. If you hold it far away and you look carefully, it kind of appears to be outside the mirror.
I can see even upside down, crazy looking things no matter where I hold it.
Right here, Bill?
That's just a blurry.
Probably not a good sign.
Well, problem is, if you get it too close, because it's such a grainy surface, you may not be able to see it as well. However, here, the take-home message is, it's a smaller upside-down image, and it is physically easy to see. You probably saw this when you did your lab on Friday. Okay? If you could physically put a piece of paper there to see it, it's a real image. If you look at it, you physically see it. You may not be able to exactly detect where it is without putting a piece of paper to find it, but you can see it. So it can form a real inverted and diminished, smaller image. And we know how to deal with the magnification, right? Calculate the magnification of this image. Call it M. M is the relationship between the object height, or the image height, and the object height. In other words, how physically bigger or smaller does it look? So this thing would have a certain image size physically and a certain object size. Now, here's the thing. With respect to the optical axis, the actual image is upside down. So we put a minus sign in there to indicate not only the relative size, but to indicate that the image is upside down. And this quantity is related to physically the image distance divided by the object distance. And both of those are measured from the origin, which would be this point right there. So let me erase some of these things now, so we can just focus, pardon the pun, on the study. So there's our mirror. Now we're back to this one focal point. Now a very curious thing happens. And you can see this when you look at that big physical mirror. If you look at it, you'll notice that as you bring the mirror in closer, what happens to your image size? So what happens to what you physically see? It gets larger. Well, let's see what would happen if we physically took this object and brought it in here somewhere. Same object, bring it in. There's H up. What do the rays look like? Same game, swing forward. One ray comes in this way, passes like that. Another ray goes to the focal point, but it's coming at such a steep angle, it gets way below the optical axis, and then it comes out this way. And now we've got a bit of a problem. And I need to give myself a good memory for that. This ray doesn't pass in this direction, at least not as a reflection. But if we follow it to the mirror and its reflection back out, it too will pass through the intersection of the two of them. Consequence is that our image now is much larger. It's over here. Distinction between the two. When I'm inside the radius, but outside the focal length to form an image, the image formed is still inverted. It's still real. It's still out here in real space. Might want to indicate that. I don't know if you've given that specifically. This is your real space. Anytime you have an image or an object out here, it's real. So we have a real, an inverted, but now it's enlarged. The distinction between the two and the tipping point is here. When you're inside the radius, you get a larger image. When you're outside the radius, you get a smaller image. There's a third type of an image that's formed with a concave mirror. I would have put that object in here instead. Because it's inside. It's not going to form a real image. It's going to form a virtual image that you're going to see inside the mirror. Now you take this, and unfortunately, if you couldn't see it, you couldn't see it. This has got a pretty steep radius of curvature, but if I bring it in close enough, I don't know, unless you need, I can see myself just fine. Got to use one eye, two eyes, I'll go cross-eyed, but if I use one eye, I can see my image upright. Oh, look at that, I'm upside down. Oh, I'm upright. So you can physically get a third upright image. That image is virtual, that image is behind me. You want to find it? Play the same game, I'll change colors. There's an show. The rays still do the same thing. One ray coming in here passes through the focal point. One ray passing through the radius. Now I'm all the way out here. Goes in, comes back out. Third ray passes through the focal point. Well, we can't get to the focal point, I have to trace backwards. So the ray that would otherwise be directed along the focal point comes out parallel. We got a problem. Ray, ray, ray do not converge. They seem like they're doing this, they're diverging, right? The beauty is, if I stand out here and look at all this light doing this, to my mind's eye, trace it all back. My eye cannot see changes and bends in the light. It traces everything back to a linear reference. Which coincidentally, if I were just to extend these rays, is somewhere back here. In other words, the rays reflect outward as though they came from a point back here. Your eye cannot tell the difference. It just sees light coming out at a particular radial direction. Your eye traces it back. This image isn't real. Call it a virtual image. It doesn't exist. But to our mind's eye, it does. For all practical purposes, as far as our observation is concerned, I see it. Now, because it's on the other side of the mirror, I can't put a piece of paper there to physically find it. But if I look in the mirror, I can see it. It's a virtual image. Anytime you have an image that's behind or inside the mirror, inside the looking glass, so to speak, to use an Allison one. It's a virtual image. And that virtual image will always be upright and either equal or larger in size than the original one, or than the original object. So why do we use concave mirrors? Remember my mom when I was a kid, she'd always sit at the kitchen table. I don't know why the kitchen table. She was always looking and putting something on her face. It's like, this big mirror, you can see it's a magnifying mirror. It's not upside down, so it doesn't throw your perception off. you just see your image is just blown up, and you've seen that effect, you know, and we've observed it. But it's not a real image. The other two are. The other two, as we saw in Lab on Friday, physical imagery. Now, in all three cases, you can always find, from a calculation perspective, where the image is formed based on where the object is and the focal point, or the focal length. So we have what we call the image formation equation. The idea behind this, it turns out, that if you take the inverse of the object distance and add it to the inverse of the image distance, this quantity will add up to be the inverse of the focal length. Let's add some reference here in case it wasn't taken care of before. When O is greater than 0, in other words, when O is positive, it is physically real. In other words, it's out in space. Now you say, well, duh. Not necessarily. You can take an image of a mirror with a mirror. You can do that, right? Have you ever looked in a bathroom that has like a folding mirror cabinet? You can see an image of a mirror's image from another mirror. So you don't have to have a real image or a real object to produce a real image, or to produce an image. And you can manipulate light in many, many different ways. A lot that we won't even necessarily talk about. But it's kind of cool if you explore it. But the key is, it's a positive value when it physically sits on the reflecting side of the mirror, and it's a real physical position.
For O, the
For
actual
O.
object?
And the same is true for I.
Didn't we just show an O that was positive on a
You betcha.
concave mirror that had
Yeah,
a virtual image?
We'll get to that. When O is greater, or when I is greater than 0, better put units here. Positive. It's real. Now I say this because what I can do from that is establish that from this origin, if you will, and I can think about it as an XY origin, the positive direction is to the left in this case. And certainly the positive Y would be this direction. So anything that's over on this side of the mirror, with respect to this coordinate 0 point, this origin, will be a negative position. If I or O are less than 0, in other words, if they're negative, they're virtual. They don't physically exist, but the light acts in the same way, because light just does. Right? We trace all diverging light back to a point of origin. Doesn't matter if it exists or not. Okay? So the distinction is when you can physically touch it or put your finger on its location when you can't. But the reference is this is negative distance, and this is negative space, and this is positive space. And that's a convention because I can be positive or negative. Hypothetical. So there's one more thing. F. F is a positive value if it physically exists in real space. So I've got F out here in front of the mirror. It's a real positive location. Okay. So I'm just going to say same for F. This is important because when F is positive, it implies a converging mirror. And by analogy, if F is a negative quantity, and it certainly can be, that implies that you have a negative focal length, or focal point that's behind you. So those are our points of reference. So to give us a sense, and we use examples here. What we think are very.
So you're referencing like O is real and I is real, not the image is real.
Yeah, he's saying that O is greater than 0, then the object is real.
Yeah.
In other words, if your object you're physically saying is out here.
That's
Now,
what
obviously,
happens.
it's on the reflecting side, so how could it maybe be behind? Actually, it can be, though. If light coming in is physically coming in, if I were to take a second mirror here, so that the reflected light would physically converge back here if this mirror didn't exist, and then I put this mirror here, that light would reflect on this surface before it ever actually gets here. But the reflection would look like it came from this point here. I know, that's bizarre. It doesn't seem right because it sort of defies our intuition, because how is this thing going this way? But the brain can't tell the difference.
Is this kind of like how holograms work? Like those holographic video games that you had like a while ago when, you know, those tabletop ones, and you had that hologram that kind of moved around.
Virtual Boy.
No, it was in the arcade.
Back hurt.
It was like early 90s or something, and it was just,
Wasn't that Virtual Boy the one you had to like put your face into?
it was the arcade.
And all the image was red?
No.
I would say no.
Virtual Boy?
The reason
Is there a
is,
It wasn't red.
well.
No, that wasn't the one I'm
stereoscopic,
talking
but
about.
just as far as where the image is formed, the object that's producing it is probably not virtual. It's probably a real object that it's reflecting. So kind of table that in the back of your mind, because it'll come back to play when we talk about lenses. So everything we talk about mirrors, we talk about lenses, we just have to put some caveat entries in. So let's look at some examples. So we take a converging mirror, and we give it a focal point f equals, say, 10 centimeters. And I put it a plus because it's a positive converging mirror. And we'll put the object, this is f, and r is about here. We'll put the object at, say, 30 centimeters. Where is the image, and what does it look like? In other words, its magnification. So somewhere out here, 20, 30, I'm going to put, here's my object, large enough to see. So we have a distance of 30 this way. And I can use SI units, or I can use centimeter units. It doesn't matter as long as I'm using consistent units for F, O, and I. And usually, physically, it's easier to see things in whole numbers rather than fractions. So this would be R. Of course, this distance is 10. And again, it's measured not from the physical surface of the mirror straight across, but from along the optical axis. The beauty of our calculators these days is that they have an inverse function, so it's a lot easier to do the calculations or keep track of it. So what we would do with the calculator, if I wanted to find I would take, well, first of all, 1 over I is equal to 1 over F minus 1 over O. And to find I would take the inverse of the difference between 1 over F and 1 over O. Now we could simplify this algebraically, but in your calculator, what you can do, in a problem like this, is you take 20, and then you use the inverse function key, the negative 1 pound. So you should have an inverse function. And I'm going to subtract that from the object distance, which is 30. Oh, F is 10, I'm sorry. The object distance is 30. And I take that whole thing get the number, and then I take the inverse of that. So I don't have to do 1 over 10 minus 1 over 30, get the answer, and then do 1 over that answer. All I have to do is enter 10 inverse minus 30 inverse, get that answer, inverse.
Okay.
So it's kind of cool to be able to do that. So, now where would it be physically if I were to look for it? Well, I'll just draw some rays in here. One should come in like that. One should come in like that. And then the third one should come in like that. So I should have functionally a smaller inverted real image. And its location should be something, without knowing anything else, I know it's going to be something greater than 10, something less than 20. Based on just how I drew it, if in fact that's an accurate statement. So if I calculated it algebraically, I would have, this is 10, this is 30, so I've got 3 30s, 3 30s minus 130, which would be 30 divided by 2, or 15 centimeters. Oh, lo and behold, it's right in the middle. It's a positive number. What's that? Now, we change O to, say, 15. And we redo the calculation. I would be, I'm going to take 1 over the inverse of 1/30th. That's not 1/30th, it's 1/10th, minus 1/15th. Again, this difference can be a positive number. That's a real value. That's a good thing. So we got 3 30ths, we got 2 30ths, and the answer would be 37. This value is larger than this value, so it should be magnified. It should be a larger image. It's a positive value, it should be real. If I were to take this object and just move it inside here, and redo the rays, that ray would not change. This ray does. And this ray look at that. This ray doesn't actually make it up there with the mirror, but it doesn't have to. That's the beauty of it. You don't physically need the dimensions of the mirror in order to make the image work, because it's just a construction. Or I could have taken a smaller object so that I would stay in the confines of the mirror. It doesn't matter. Either way, there's my image. Now, it isn't quite there. It's because I can't draw it. Save my life. If I could, by golly, this would be down here. It would all be over there. Now, before we take a break, let's put the object at, say, 5 centimeters. There's our optical axis. This is F, and this is R. I'm going to put my object right up through this way, which requires that the actual reflected light's going to do this. By the way, there's a 4th ray that we can use for reference. It's kind of nice. Might help in this particular case.
You just said that here.
Also also not a regular distance. And when this one is more untenable to get to, because it's, well, in this case, it was kind of an untenable ray. We could just use this fourth ray. Let's see if we back on itself like that. And the fourth ray would go up like that, something like that, and it would come out this way. So again, we're up against a diverging light coming out of the deflection. And if we trace these rays back, our image again should be there. And rather than use that last ray that I drew, I took this ray. Back. Perfect.
So it's refracting through.
Yeah, I gotta try
It's
this
not
out again.
refracting.
This is not working for me at all.
It's not refracting.
I can't imagine. I don't have a good imagination.
Me neither.
Isn't that beautiful?
I have to.
They
I
all
gotta draw it
together.
perfectly. I need.
Your
I'm not
eyes
At the-
imagining, I guess. I'm just-
projecting by
I need to draw it
following,
perfectly.
tracing back.
So my eye just looks at all of this stuff coming back to
Yeah, I
a
can't- I
single
mean-
point of origin there.
That's the problem with all the waves for me. And
So our eye just doesn't know the
Optics.
difference.
say we were doing like bonds
So
and
the
stuff, but
objects
so
in
it's
that mirror.
talking about real solid objects.
Yeah.
And I could see and imagine how it's going.
I'd say it's further away.
Yes.
I just follow the
When
rules.
we get to this,
You have the mirror.
it'll be
Yeah.
closer than it
Right, like
appears.
this.
I need to see this. I can't.
Optic appears closer.
Close enough.
Yeah, I can do the
In this
math all
case,
day.
the object is closer. Oh, I'm sorry, yeah, object is closer than it physically appears. It seems like it's farther away.
It's more
But
studies
it's
on it.
Larger.
But it's,
But this distance is larger.
it's farther away.
So I hate things that I can't
If you
see.
do the math,
That's why I'm happy
negative
with this
5
video. I'm just
centimeters.
gonna.
Huh?
I'm gonna listen
Oh, with
to
these
him.
numbers, it comes out to
I'm
negative,
just
of
gonna
course.
listen to him
I
say this again, and
hate
then
cracking numbers, sorry.
I'll follow.
Oh.
Five or 10.
A little
Well,
easier.
actually, in this case, it doesn't, it's not even farther than it appears, it's actually the same spot, which means,
1 over f minus 1 over o,
So
it's
1 over
1/10
10
minus
minus
1/5, negative 1/5. Or no, I'm retarded.
That'd be one.
I was gonna say, I
That's too dense.
didn't do my ray diagram incorrectly, so that can't be the case, it's gotta be further out. Okay, that makes more sense, so it's about, oh, look at that, it's actually.
Look at that, it's double, it's right at the focal.
Yeah. Okay, well, we can always calculate it, right? It's hard to do ray diagrams without a meter stick